So in this section, we're going to build up to Gauss's law, and it involves a Gaussian surface. And we're going to talk about what exactly that means. But first, we have to introduce this concept of flux, specifically electric flux. So instead of asking, what we've kind of done so far, given a collection of charges, what electric field is produced at a given point? That's kind of the question that we end up asking and solving. We can actually flip that question around and ask, given the electric field around a collection of charges, what's the arrangement of charges producing that field, right? So if we know the electric field around a thing, then what must be the source that's producing it? To answer this question, we need to know the electric field at more than just a single point near the charge distribution. We can imagine taking a closed surface, some surface area of arbitrary shape that fully contains a volume. That's kind of like what we're looking at here. So say you measure the force produced on a test charge, Q naught as always, as you move it around at all points on that imaginary closed surface of arbitrary shape. What you gain from this exercise is a map of the electric field on that surface, right? Map of the electric field, which would be force per charge, per unit charge. And it turns out that with this electric field map on your arbitrary imaginary surface around the charges, you can actually determine exactly the distribution of charges that are inside, which feels kind of counterintuitive, right? So you choose the surface. It doesn't have to be some perfect sphere at some perfect radius around. You can have just some weird arbitrary surface, just like what you see here, as long as it fully encloses the collection of charges or charge distribution, and you know the electric field at all the points. So this imaginary surface on which you measured this electric field at every point, that's called Gaussian surface. The flow, quote unquote, of the electric field either into or out of your Gaussian surface is called electric flux. So thinking back to electric field lines, if we were to enclose this charge with a Gaussian surface like this, there would be outwards flux of this surface, right? At all these points, there's outward flux. If we were to enclose it, this one, there's inward flux over here and outward flux over here, right? And this is no different than if there were one, there's just more flux, right? So the density of the field lines is kind of trying to indicate the strength of the electric field. And so there's more, right? So this is the concept of flux, the amount of stuff going through a surface, right? So the flow of something either into or out of some enclosing surface. So, to describe flux mathematically, we'll start with fluid flux, right? So we kind of talk about electric field as sort of a flow. So we'll talk about if we're actually literally talking about a flow of liquid, like of water. If we have some ring inside of some thing that has water flowing in it, right? So this is like some stream of water, right? And the water is going through this ring. Say the water is traveling at some velocity v, and the surface area of this, right, this ring is A, we'll say. The volume flow rate, volume of water per unit time that passes through the ring is given by the flow speed, v, multiplied by the area. So delta v per delta t is given by v times a. Well, that's all well and good, but what if you have a ring that is kind of tilted a little bit? That's terrible. Something like that, right? It's tilted. And so you have it being at some angle relative to the vertical, which it is not. Call that phi. Well, now, in order to describe the area, we have to give it some vector. So the vector normal to that surface would be vector A, is what we're going to say. The area, right, you can still say that there's some area A, but in vector form, we're going to use the normal to that surface to describe it. And the water still flows with velocity v. That hasn't changed. So this vector A, that's just the way of describing it. And we have this vertical component here. Oh my gosh. We have this vertical component here that I will describe as A perpendicular, which is equal to A cosine B. And so all that's just to say that if we have a tilted surface at some arbitrary, vector A, then the flow rate is given by the same thing, delta V over delta T, but this time it's the component that ends up making it through and at the same direction. So you have VA cosine phi. So thinking about this, if phi is 90 degrees, then the flux is 0. That would be the situation where you have the ring that is completely flat, right? So no water would be flowing through that thing. It would be flowing above it and below it, but not through it. So that is the case where this phi angle is 90 degrees. So flux is 0. So this makes sense. And if phi is 0, then it's 1. So then it reduces down to this equation. So this makes total sense to us intuitively if you think about that. So now, if you want to express this in a little bit better way, right, what we're asking is how much something is parallel to something else, how much something is in line with something else, right? So we have a vector A and a vector V, right? A given by perpendicular to the surface. And if they are totally pointing in the same direction, then you have this situation over here on the left. And you have the maximum amount of flow, V times A. If they're pointing orthogonally, right, then you have this situation over here. If A is 90 degrees from V, then there is 0 flux through that ring. So what is a vector way of expressing how parallel two vectors are? That's the dot product. I don't know if anybody's ever walked through that with you, but it's the dot product, right? And so if you have A dot V, you have A times V cosine of the angle between them. And so if they're directly in line with each other, then you get the maximum value. And A times V times cosine the angle between them, if that angle is if that angle is 90 degrees and they're perpendicular to each other, then you get 0. So that's exactly what relationship we want here. So in its most general form here, the flow rate per time, right, flux, is given by V dot A. This isn't just multiplied, it's vector multiplication, the dot product. So now turning back to electric flux, it's going to be a similar concept, but we just replace the fluid flow with the electric field, E. And we assign actually a new symbol to the electric flux, and that is this symbol here. So it's the capital Greek letter phi, or phi, I don't know, I think phi, with a subscript E to remind us that this is an electric field. So this is equal to, we're just replacing, there's not water flow, it's electric field, quote unquote flow. So E dot A, right? So if we had a Gaussian surface, right? We had this Gaussian surface, this kind of acts as each like area point on this thing, like what it's showing here actually, has some area, delta A, right, because it's some bit of area, and it has some flow through it. And so in this case, this is the flow in some weird arrangement. Who knows what the charge distribution is? Maybe it's curving around and, right, curving around and doing this kind of a thing. Who knows? But that's what they say it is in this little random example. And so we want the component that is parallel to the area normal vector, right? And so E dot A. All right, so now Gauss's law. The whole reason we did this is Gauss's law. I'm going to go ahead and do this concept of flux, conceptually, as well as a little bit mathematically, will be important. Conceptually, very important. So Gauss's law is actually an equivalent and alternative expression of Coulomb's law, which sometimes frustrates students because they say, well, if we already know it, then we already know it. Why are you telling me this? Valid, right? But turns out it helps you solve problems that you wouldn't be able to very easily solve with Coulomb's law. So some things are a little bit easier solved with one tool versus another, even though you can use a screwdriver to bang in a nail, right? Probably best to use a hammer, even though maybe that's not the best analogy because those aren't equivalent, but they can both bang on things. So anyhow, it provides another way of doing things. So as we know, the electric field of a single positive point charge Q is given by KQ over R squared, right? This R, you're like, well, what the heck? Where does the R come from? Just to remind you, this is some point charge Q, right? And that is the source, right? Oops, that's the source, wherever that is. And you have to pick some point for the electric field to be evaluated. It's not just in general, because it's different at different points, right? So this is some point, and so R is the distance from the source to the point, right? So of course it's going to have different values depending on where you choose. Look at how dynamic this situation is. So E is at a very specific point. So if we enclose the point charge with a spherical Gaussian surface, right? Of course, in general, it can be any surface, but in order to show this without using calculus, we're going to choose a spherical surface. We can make it of arbitrary radius, r, that's no problem. And we can compute the electric flux through that surface. So, right, so we have this thing, and we are going to create a Gaussian surface of our choosing that is spherical. I'll do a better sphere here. Spherical about it. You can even think of it. Let's see, how can I do? Yeah, look at that. Nice and spherical. Boom. Around that surface of some distance r, right? So if we wanted to compute the flux, so this is our Gaussian surface. The flux is printed right up above. Phi sub E it's a silly phrase, is equal to, again, E dot A, which is equal to, so A points radially in all directions, so that's one of the things that the sphere makes easy. So the area points the same direction as the electric field in all directions, basically, right? So at any given point, right, you choose a little bit, the area vector is going to be normal to the surface, which is a sphere, so it's always radially out. And also, since this is just some, positive test charge, the electric field is going to be pointing also directly out. So at any point you choose to evaluate, those two vectors are always in line. And so, therefore, cosine of 0 degrees. So it's just very simply E times A. And we know what E is. It's KQ over R squared, R being our radius. I'm going to get rid of this point there because it's irrelevant. We're evaluating at the surface of our sphere. And we know what the area is. The total area of our Gaussian surface is the surface area of a sphere, which is 4 pi r squared, right? And this looks like maybe it's not going to work out. I mean, okay, our r's cancel, so that's nice. So we have kq times 4 pi. Well, what the heck is that? Well, do you remember what k actually was? All the way back at the beginning of our lecture, we identified what k actually was. 1 over 4 pi epsilon naught. So let's bring this down here. So this is equal to 1 over 4 pi epsilon naught times q times 4 pi. Woohoo! Those 4 pi's cancel. So what we're left with is q, the amount of charge inside this Gaussian surface, right? This is of a point charge. It works out in general, it turns out, but this is all I can show you without using calculus, divided by this weird permittivity of free space value. So the charge enclosed divided by epsilon naught, which is, you'll have to maybe trust me, a beautiful and remarkable result. And it works in general for any charge distribution and any Gaussian surface. Calculus can show you all of the ways in which, all of the combinations, but we don't get into that here. You'll just have to take my word for it and accept this spherical case as an example that shows you the result. So if you just kind of, eliminate the whole journey we took, what we found is that the total flux, electric flux through a Gaussian surface, arbitrary Gaussian surface, is equal to Q divided by epsilon naught. And if you have some other charge distribution that isn't a point charge, like I said, it also holds. It's just the total charge of everything that's enclosed. So in general, this is Gauss's law. In general form is the total electric flux, right, into or out of the Gaussian surface of any arbitrary Gaussian surface is equal to, I'm going to write a capital Q, and I'm going to write enclosed, Q sub enclosed, divided by epsilon naught. That is Gauss's law. Very different, you would agree, from Coulomb's law, which is supposedly synonymous to. So you can see how different of a tool it might be to solve for things. All right, so that is the end of our first lecture. Please make sure that you review all this stuff, do all the homework, keep up with the course, and we'll move on with our next lecture next time.